Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today our topic is implicit differentiation. So we're going to talk about equations and how to take derivatives of these equations, but they're not going to look the same as equations or functions that we worked with in the past. So to get our feet wet today, we're going to start off by trying to take the derivative of this equation right here. And so pause the video, see if you can take the derivative, and then come back and join us for a discussion. Okay, so obviously right away you may have seen, well, the y is not by itself, right? We know how to take derivatives of functions where we have something like f of x equals 4x squared, maybe plus sine of x. Or we've had y equals something like e to the x, maybe times cosine of x. Right? We could certainly take both of those derivatives. The problem is the y has always been isolated. And in this equation, the y is mixed together with our x's. Now we know how to do product rules where we have two functions of x, like right here, but we don't know what to do when it's, e to the x and then cosine of y, right? Because both of those functions are not functions of x. So maybe one thing you thought of was, well, maybe I could try to get the y's by itself, right? So maybe you move the 3x cubed to the other side. So you had negative 2y squared plus 10xy equals 10 minus 3x cubed. Maybe you factored out a y, so you had y times a quantity negative 2y plus 10x. But as you keep going, right, you're still unable to isolate the y's. Now you have a y outside as a factor, and then you have y inside the parentheses as part of that factor. So we're not even going to keep going with this because we, again, don't know how to still isolate that y. This is a type of equation called an implicit equation. Implicit. Let's make that a little bit neater. It's a little better. This is when the equation is not solved for one of the variables, which makes it difficult to tell if your equation represents a function, right? Because a function would have to pass the vertical line test. There can't be two y values for any x value. And when the y is not clearly by itself, it's sometimes hard to tell whether it represents a function or not. Explicit equations are the opposite. These are equations where the equation is solved for either x or y, and the other side is completely defined by one variable. And, there's three examples below, ones that we're comfortable working with and taking derivatives of. Sometimes it's easy to rearrange an implicit equation to make it explicit. Right? Sometimes it might be easy to isolate that y. So you could pause the video, see if you can isolate y for number 1, and then go ahead and take the derivative with respect to x. So obviously I would just add the y to both sides, subtract the 3, so I'd get y equals 5x squared minus 3. I could take the derivative of both sides with respect to x. And we end up getting dy dx, or you could say y prime, is equal to 10x. So in this case, it was easy to take the derivative of this implicit equation because it was quite trivial to get the y by itself and then go ahead and take the derivative. But as you can see, that's not always the case from what we saw in our equation up above. All right, let's go ahead and take a look at another problem. Like we said, some equations are not easy to solve for y, like the one from the introduction, which means we need a new technique for taking the derivative. And this is the process called implicit differentiation. Taking the derivative of an implicit equation. Before we show you exactly what it is, let's think about why this could be helpful. And we kind of looked at it up above, but let me give you another example, this time with a graph. So we have an equation of a circle, x squared plus y squared equals 25. And we want to figure out the slope of the circle at the point 3, 4. So without knowing how to do implicit differentiation, we would have to try to isolate the y. This equation is not too difficult, right? I can just subtract x squared from both sides and take the square root. Let me do that up here. So I have x squared plus y squared equals 25. That means I get y squared equals 25 minus x squared. And then I could take the square root. The only thing I have to be careful of is that I'm going to get y equals the positive root. So y equals the square root of 25 minus x squared. And I'm going to get y is equal to negative the square root of 25 minus x squared. So there's two functions of y essentially. One that is the part of the circle above the x-axis and one that's the part of the circle below the x-axis. So if we take the derivative, right, well, we've got to know which y equation or which y function to take the derivative of, right? Do we need to take the derivative of the positive root or do we need to take the derivative of the negative root? In this example, it's not too bad because we know that the point 3, 4 falls on that upper half, and we should be able to identify that that equation is going to be the positive root, right? Because we need positive y values. So we could go ahead and take the derivative of y, the first y. Let's just do that real quick. I'm going to rewrite it. So y is equal to, I'm going to rewrite it using exponents because this could be a little bit easier when we do the chain rule, at least to understand, I think. So dy dx, or this time we'll just say y prime, is equal to 1/2 times the quantity 25 minus x squared to the power of negative 1/2 times the derivative of the inside, because we're using the chain rule, times negative 2x. What this ends up equaling, we end up, the negative 2 and the denominator simplify. So I get negative x all over the square root of 25 minus x squared. And if you're not sure how I got that, go ahead, pause the video, and work through the chain rule yourself. Now I could go ahead and substitute in my x value, right? So this derivative at the point 3, 4, let me substitute 3 in for my x. So I get negative 3 all over the square root of 25 minus 9. That gives me negative 3 over the square root of 16. Oops, finger was on the mouse. Which gives me negative 3 over 4, which would be the slope of this tangent line. And that makes sense, right? This we know this tangent line is going to have a negative slope, so negative 3/4 would seem to be something that would be reasonable for that slope. However, you know, this was a decent amount of work, right? We had to isolate the y. We had to figure out which equation to take the derivative of. Then we had to go ahead and take the derivative, and then we had to go in and substitute. This was a relatively easy equation to do all of that with as well. So let me just clear this and show you what's down below. Right? We could run into something like this, where we're not going to be able to isolate the y, right? We're just not going to be able to do it algebraically. So we're going to run into some problems which isn't going to allow us to take the derivative, or maybe we can isolate for y, but it's going to be very complicated to know which one to use for our derivative, which equation to actually take the derivative of. So this is where implicit differentiation comes in handy. Remember that we know that the derivative's value should be negative 3 over 4. But now I'm going to show you how to do it using implicit differentiation. And keep in mind that this is just the chain rule. All right, we're going to show you what I mean by that in a second, but it is an application of the chain rule. What I'm going to do is I'm going to take the derivative of both sides with respect to x. Okay, so I can break this piece up, right? Derivative rules. I can take the derivative with respect to x of x squared and add that to the derivative with respect to x of y squared. The right-hand side's pretty easy. The derivative of x with the derivative of a constant with respect to x is just going to be 0. This quantity should be fairly straightforward. We've done that quite a bit, so I should just get 2x here. This next piece, though, the derivative of x with respect to, the derivative of y squared with respect to x is a little different to think about. All right, there's no x's here. However, we're going to assume that y is a function of x, right? We could rearrange this equation up here to get y by itself and then for y to be a function of x. One thing that may help you think about this is instead of just saying y squared, right? This is really a function y of x squared, assuming that y is a function of x. So, right, we're going to apply the chain rule here. If I was going to take the derivative of this right here, right, well, I would take the derivative of the outside function, so I'd get 2y of x times y prime of x, or dy dx, right? I could say dy dx, or I could say y prime of x. Actually, let me put that here just to show you the relationship. Right, y prime of x is the derivative of the inside function, whereas 2y is the derivative of the outside function, something being squared. So this could be 2y of x times dy dx as well. Which means over here, I'm getting 2y times dy dx. I don't know what the derivative of y of x is. I mean, I could use one of those from up above, right? Up above, when we simplified, or when we isolated y, I got the square root of 25 minus x squared, and y equals the negative square root of 25 minus x squared. So if I really wanted to, I could take the one that corresponds with the point that I'm trying to find the derivative at. I'm trying to find the derivative at 3, 4. So I could take the derivative of this equation, which we already did, and I could substitute in for dy dx. But we've already done that. That's why I already know what dy dx could be, right? If I'm just given a random implicit equation, right, I'm not going to know what dy dx should be because I didn't go back and do all that work previously. So I'm just going to leave it as dy dx. And now my goal is to isolate the dy dx, the derivative of y with respect to x. So I'm going to subtract 2x from both sides. I'm going to divide both sides by 2y. So I get dy dx is equal to negative 2x divided by 2y, which ends up being negative x over y. Okay, so that's our derivative when we use implicit differentiation. Now, remember, we're trying to find the derivative at the point 3, 4. I'm going to get rid of this. This is not going to take us very long at all, right? Because it's a fairly easy derivative to substitute into. So at the point 3, 4, well, we get negative 3 over 4, which is the same derivative we got from up above when we did all that work to isolate the y and then take the derivative that way. You may say, that first way still doesn't seem too bad compared to this way. You're right, it's not too bad for this specific implicit equation, right? But this is a fairly straightforward one. We're going to take a look at one below where you definitely want to use this method compared to trying out what we used above. So let's walk through another example. I'm going to continue to hone in on how this is the chain rule to help you guys hopefully understand this. So it's clear. Okay, so now we're given a really wacky equation, right? And this would definitely not be a function because it doesn't pass the vertical line test. We're going to use implicit differentiation to find the slopes at 2 points, 2, 0, and 1, 1. I would encourage you to pause the video, see if you can replicate what I did up above. Even if you don't understand it fully, the inner workings of what's going on, you could still try to use the algorithm of implicit differentiation to find the derivative. So pause the video, then come back once you've attempted that. All right, so we are going to start with y cubed, that's squared, y cubed plus y squared minus 5y minus x squared equals -4. I need to take the derivative of both sides with respect to x. D over dx. So I'm going to get 3y squared, that's the derivative of the outside, times the derivative of the inside, which I don't know what it is, but we can call it dy dx because we're assuming that y is a function of x. Right, again, I'm going to write this out over here. If I had y of x cubed and I wanted to take that derivative, well, I take the derivative of the outside, which is something being cubed. So I would get 3 y of x squared times the derivative of the inside. The inside function here is y of x. Derivative of y of x would be dy dx. So if you think of that y as really being a function of x, which it is, where they're just not writing that of x in there, it's implied, then hopefully it's a little bit more understandable. Let me keep moving on. Look at our next term. The next term is y squared. So I get plus, let's make that a little bigger. So I get plus 2y, and then times the inside function, which is dy dx, times the derivative of the inside function. Next term is -5y, so I get -5, that's the derivative of the outside function, times the derivative of the inside function, which is dy dx. My next term is just -x squared, so that's a very easy derivative, just -2x equals 0. So you'll notice whenever I'm taking the derivative of a term that just has a y in it, right, I'm going to get a dy dx because I'm going to have to use the chain rule, first take the derivative of the outside function times the derivative of the inside function, which is going to be dy dx. Now I'm going to isolate the dy dx. So I'm going to add 2x to both sides, 3y squared dy dx plus 2y dy dx minus 5 dy dx equals 2x. I'm then going to factor out the dy dx from all the terms. So dy dx times the quantity 3y squared plus 2y minus 5 is equal to 2x. And now I can just divide everything by this quantity right here. So I get dy dx is equal to 2x all over the quantity 3y squared plus 2y minus 5. So it may seem like a lot of work, but it's a lot less work than trying to isolate the y in the first place. And now it's very straightforward. I just need to substitute in 2 everywhere I see an x, right? I'm finding the slope of the tangent line or the derivative at 2, 0. So everywhere I see a x, I replace it with a 2. So at 2, 0, that is going to be equal to 4 over -5. Because those 2 y terms in our denominator are just going to be equal to 0. Let's see if this makes sense. If we go to the point 2, 0, it does make sense because we should have a negative slope for our tangent line. And we do have a negative slope, 4 over -5. You could also find the derivative at 1, 1. Here, we have something different going on. It looks like we should get a vertical tangent. So you can think about what the derivative's value should be there. But at 1, 1, well, we get 2 in our numerator. We get 3 plus 2 minus 5 in our denominator, which gives us 2 over 0, which is d and e, or undefined. And I would like to do one more problem, just to show you how to invoke the product rule when we're using implicit differentiation. So we're going to take a look at one of the ones down below. Just clear this. And let's take a look at number 4. So for these, you're just being asked to use implicit differentiation to find the derivative dy dx of each equation below. So we don't have to substitute in and find the value, we just have to find the dy dx. So let's go ahead and take the derivative of both sides with respect to x. And you'll notice that we see an x and a y being multiplied together on the left-hand side. So we treat this as a product rule first, and then as a chain rule with our y. So let's use different color. So product rule, I'm going to take the derivative of my 2x, which is 2, times my other piece, which is y, plus my 2x times the derivative of y, which in this case is just dy dx. That's going to be equal to, this other side's what we did up above. I'm going to get 6y times dy dx after using the chain rule, plus 2. So really just the left-hand side was different. I just wanted to show you how we use the product rule when using implicit differentiation, especially when we have an x and a y being multiplied together. Now again, I'm just trying to isolate the dy dx, so I'm going to get those terms on the same side. So I'm going to bring the 6y dy dx over to this to the left side, so I get 2x dy dx minus 6y dy dx. I'm also going to subtract 2y from both sides, so I'm going to get 2 minus 2y. Then I'm going to factor out a dy dx on my left-hand side. So I'm going to get dy dx times the quantity 2x minus 6y is equal to 2 minus 2y. And then just divide everything by the quantity 2x minus 6y. So I get dy dx is equal to 2 minus 2y all over the quantity 2x minus 6y. Now for an open-ended question, this would be sufficient unless they said to simplify. For a multiple choice question, they would certainly have the simplified version. So you'd have to factor out a 2 from both the numerator and the denominator and simplify. I'll just do it in 2 steps. So I get 2 times the quantity 1 minus y all over 2 times the quantity x minus 3y, which gives me 1 minus y divided by the quantity x minus 3y. So that would be our dy dx for number 4. Okay, we'll get to some of these practice problems in class, but you're certainly free to attempt some on your own to get some more practice in. That's going to do it for this video. As always, enjoy the rest of your day, and I look forward to seeing you next time.